Sorry. Good morning, everyone.
Good morning, sir.
Good morning, sir.
Yeah, today is lecture number 9 of this advanced concept in steel technology, and we were in the topic that is about strengthening mechanisms. Hmm. And already we have discussed about many strengthening mechanism, and today the topic is on strain hardening or work hardening. Tapas, you want to speak something? Okay, so the what is strain hardening exactly? So you can see strain is one term and hardening is another term. Hardening means we know that strengthening. We have to increase the strength of the material, right? And strain here means we are giving strain to a materials. That means we are doing plastic deformation to a materials. The moment we are doing plastic deformation to a materials, so that is a strain in the material, right? Because if you remember stress versus strain axis, strain is nothing but change in length per original length, right? So we are changing the length of the materials, right? Exactly. So due to which a hardening will be there, strengthening will be there. So that is called strain hardening. And the strain hardening is also called work hardening, right? So here work represents your plastic deformation, right? We are deforming the metal plastically. That means suppose we are doing rolling, we are doing forging, we are doing extrusions, all are metal working processes. So during this metal working processes, hardening will be there or strengthening will be there. But the point you have to remember here is this should be cold working, not exactly hot working, right? So now, can anybody tell me why, if we do hot working, then the strengthening will be not there? What may be the reason? What may be the reason? If we do hot working, there will be no strengthening much. But if you do cold working, there will be a strengthening here, as I told.
So due to hot working, maybe the dislocations will be removed or the
Yes,
defects will
yes,
go
very
away.
good, very good. Yes, because in case of hot working, that means the temperature is very high, that is above the recrystallization temperature. And you understand when the temperature is very high, the diffusion starts, right? Diffusion phenomenon starts. That basically vacancies will generate. A lot of vacancy will generate in the material, and diffusion of this vacancy towards dislocation will be there. And what happens? The dislocation climbing will be there. And the moment dislocation will climb, they will get absorbed by the grain boundaries basically, or many other phenomena, diffusion phenomenon will happen, due to which the dislocation will get annihilated, right? Disappearance of the dislocation will be there, right? So strain hardening, you understand, that means the strengthening due to dislocations basically, huh? Dislocation, here what happens? Dislocation interaction will be there. Dislocation interaction. The dislocation will interact with other dislocations, right? So then basically you understand around the dislocation there is a strain field will be there, right? Similarly, many strain fields will be there around the dislocations. So due to interaction of strain field of one dislocation with other dislocations, there is a strengthening, right? So that is called strain hardening or work hardening. That means you understand the moment you are doing working on the materials, you are doing cold working, for example, on the materials. So what will happen? The lot of dislocations will generate. Huh? We'll see that soon. We have a very interesting images. We'll see that soon. Strain field of dislocations. Relax. If you remember, the same strain field or stress field repels and opposite stress field or strain field attracts, right? Okay, fine. I'll show you a very good image which will tell you about the strengthening due to or hardening due to this strain or due to this dislocations, or work hardening. Just look at this one. This is a nominal stress versus nominal strain plot. Hmm. So suppose this is when we are doing loading on the material. You can see this is the plot, and we can see this is the yield strength, and this is the ultimate tensile strength, and finally it will go to fracture point anyways. So you understand this is the yield point here. That means if you remember, above this point, plastic deformation starts, right? So suppose you are deforming a material to this point, for example, it is sigma A, for example, up to this point. That means already the material has deformed plastically, and the stress is here, for example. This is the stress point. Now suppose I will unload the materials. You can understand this arrow mark is showing unloading, right? I will remove the load. So I am unloading the materials. This is over. The moment again, if I will load the materials, right? What will happen? You can understand this when I will again load the material. This is your new yield strength, sigma ys. This is the new sigma ys, right? Originally, this is your sigma ys, but after deforming the material to this point and unloading it, again you are doing loading on the materials, the new yield point will be this one. And similarly, if you then deformation will be going on, and a new white UTS will be coming out from this one, and finally fracture will happen. So you understand what is the conclusion? Conclusion is, if you deform a materials first, then we will have a particular yield strength and particular tensile strength, right? But if you unload the materials before UTS and again we will load the material, right? Then again we will get a new yield strength and new UTS. Fine. So that means the strength are increasing due to this deformation, right? So also here it is written, yield strength of the deformed metal is higher than the undeformed metal. So you can do an experiment to justify the strain hardening phenomenon, or to justify dislocation strengthening or quark hardening. You can perform two experiments. Very easy experiment. You take a piece of steel, for example, you cut it into two pieces. The first piece, you do a tensile test on it, and you will get a yield strength and UTS, right? What happens to the next piece of metal? You do, suppose, hammering on it, right? You do hammering or you do forging on it. You apply some load and you deform it plastically. Then you do tensile test on that. So you will get what? You will get that you have a higher yield strength and higher UTS in that piece. So it is written over here. So that is strain hardening or work hardening. I think you people have understood well. If you have any doubt, you can ask me in between. Next, to justify that also, I have another interesting figure here. Just look at this figure. You can see in this direction, this is the percentage cold work. This is the percentage cold work direction, and this is the strain axis, and this is the stress. So what exactly this figure is showing? You can see, suppose this is 0% cold work. This at this point is showing 0% cold work, and I am doing a tensile test. So I will have a stress versus strain curve like this. Second, suppose this point is showing 10% cold work. I will get a stress versus strain curve like this. Suppose this point is showing 20% cold work. So this is the stress versus strain curve. I am doing 30% cold work. So this is the plot. I am doing 40% cold work. This is the plot. I am doing 50% cold work. So this is the plot. Stress versus strain plot, right? And percentage cold work means, you understand, this is nothing but the initial cross-sectional area of the specimen minus final cross-sectional area divided by initial cross-sectional area into 100. This is same as your reduction in cross-sectional area. Okay, let me ask. Okay, Subhasri, can you tell me, when we plastically deform a material, what happened to the cross-sectional area and what happened to the length? Subhasri, you are there?
Yes, sir.
Yeah, can you answer this one? What happened to the cross-sectional area and what happened to the length of the material when you deform a metal plastically?
Length will increasing with decreasing cross-sectional area.
Yes, right. Subhasri, when we do a tensile test, what happens to the cross-sectional area of the gaze part, and what happens to the gaze length when we do tensile test?
Length will be increasing.
You have seen that video? You have attended that class when I have shown you a tensile test video?
Yes, sir.
Yeah. So what happened to the length and what happened to the cross-sectional area? Yeah, you can answer quickly. Length is increasing or decreasing, or cross-sectional area is increasing or decreasing? Bhagyashri, what happens to the cross-sectional area of the specimen when you deform a metal plastically? And what happened to the length?
Sir, increasing.
What will increase, the
What will
length or
increase, the length
cross-sectional
or
area?
cross-sectional area? Cross-sectional area.
Cross-sectional area will
Cross-sectional area
increase?
will increase?
What you are
What you
saying?
are saying?
The length will increase and
Length will
cross-sectional decreasing.
Who told length will increase and cross-sectional area will decrease? I think I have to go back and have to show you the video again.
Sir, length increasing kariyo, cross sectional
Yes,
area.
obviously, length will increase. You all of you have seen that video. I have shown you the video. What I can show you more? You are applying a tensile load and the length is increasing. You have seen, and finally a fracture will be there. This is a simple thing you are not saying. You cannot answer a simple thing. What more I can show you? Okay. Anyways. Okay, fine. Can you people tell me now? I have explained everything: the percentage cold work and the strain versus stress plot for each percentage cold work. So, tell me what is happening here. Can anybody figure it out? What is happening with the percentage cold work? What is happening to the stress versus strain curve?
Sir, strength increasing करछि, ductility decreasing करी जाउछि.
Okay, fine, very good. Let me ask others. Okay, Manas Ranjan, can you tell me what is happening to this?
Ductility decrease.
Who is saying? Subhasri, you want to speak?
Sir, in here the ductility is decreasing.
Acha, how can you justify the ductility is decreasing? How can you justify? Yeah, this is visible, but can you justify that?
Sir, fracture da strength increase time re fracture da jalti hi jaisi tapare.
Yes, Tapas, you are absolutely right. You can see the fracture stress. Subhasri, can you tell me which axis will show you the ductility? The stress axis or strain axis?
Sir,
Okay,
strain
Bhagesh.
axis.
Strain axis, very good. Strain axis will show you the ductility. So what is happening? Can you tell me, justify that? How ductility is decreasing, you are saying? Okay, Subhashir, can you tell me what is this Y, what is this U, and what is this F? In a stress versus strain
So
curve.
y is yield point.
Yield strength, very good. What is U?
U is the ultimate tensile strength.
Very good. What is F?
A fracture point.
Fracture stress, yeah, very good. So now can you justify how with increasing in the percentage cold work, you are saying the ductility is decreasing? How? Yes, Subhasri, you can speak. Yeah. Make yourself confident. We have enough time to discuss. Yeah, look at the fracture stress. What is happening to the fracture stress? If you draw a projection to the strain axis, what is happening?
The yield
Yes.
strength and the tensile strength are increases at certain
Very good.
point, and fracture stress it is
Decreasing.
ductility decrease.
Okay, that is my question. How you will identify the ductility? What you have to do? You have to draw a projection, right, to the strain axis at the fracture stress
Yes, sir.
point. Yes, very
Yes,
good.
sir.
Okay, fine. Now you understood. Okay, very good, very well. So now you can see, everybody can see, with increasing in the percentage cold work, we can see y is increasing. Initially, y is this one. Y is increasing. Y is increasing. You can see, and u is also increasing, right? So conclusion is what? If you deform a metal by cold working process, that means the deformation is happening below the recrystallization temperature or in room temperature, for example, there is an increasing in the yield strength, there is an increasing in the tensile strength. But you can see the fracture is happening quickly. Initially fracture is happening here, but now you can see fracture is happening sooner and sooner and sooner. If you draw a projection to the strain axis, that will show you the ductility, because ductility means from this point to this point, right? Initial ductility is this much, but this is basically, you can see, this is undeformed specimen, but this is the stress versus strain curve of deformed specimen. These are deformed specimens, right? The fracture is happening very soon here. If you draw a projection from here to here, this is going down, you can see. From here to here, this is going down. From here to here, this is going down. So there is a problem actually, huh? There's a problem. What kind of problem we can face? If you have severely deformed the metal, the percentage cold work is more, then you should, sometimes you cannot, you will not get any warning before fracture, right? So this is one of the problem you can face, because there will be a reduction in the ductility. Okay, everybody have understood this plot anyways. So now let me show you another stress versus strain plot. Basically this is a true stress versus true strain plot. Fine. You can see this is for metal B, this is for metal A. So here you can see metal A is hardened more, metal B is less hardened. So this is there is a relationship, you understand this one. Sigma true stress is equal to K epsilon true to the power n. So where n represent your hardening exponent. So n have different values for different metals or different alloys. And this is 0.15 for some steels and 0.5 for some copper alloys. So you can understand from this figure that different metals can be hardened, strain hardened differently, right? That means suppose steel is hardening to a certain extent, copper may not be hardened to a certain extent, or it may harden more and less, right? So anyways, so this is one part. And you understand how to get this n. Hardening exponent can be obtained by taking a slope in the plastic region. You have to remember that. Slope in the plastic region will give you hardening exponent, that is n. And if you remember, if you take a slope in the linear region of a stress versus strain curve, what you will get? Can anybody tell me? Already we have discussed that while we have discussed about the properties of metals. If you take a slope in the linear region of the stress versus strain curve, what kind of property you will get? Let me ask. Dasashwani, can you answer? If you take a slope in the linear region of a stress versus strain curve, what kind of property you will get?
No, sir.
You are confidently saying no. Have you attended the previous lectures when I have shown you those properties of a metal by the help of stress versus strain curve? You have attended those classes?
Yes, sir.
Yeah, you are confidently saying yes, but you cannot easily. Okay, let me show you again. Okay, this one, for example. This is the linear region. This is the linear portion, right? If I will take a slope here, so what I will get? If I will take a slope here, what I will get? Just tell me. If I'll draw a slope here, what I will get? This is the stress axis and this is the strain axis. Slope means you understand. Suppose dy by dx. or y by x, simply you can say. Y-axis is stress, x-axis is strain. I have given you enough enough your idea. Now can you figure it out? Vijay, what it shows? Slope in the linear portion of a stress versus strain curve.
Sir, Young's modulus.
Young's modulus. What is the other names? What are the different names of Young's modulus?
Modulus of elasticity.
Modulus of elasticity. Very good. Any other
Elastic,
name?
elastic modulus.
Yeah. Any other name? Generally, we used for a material property, mechanical property.
Young's modulus.
Stiffness.
Already he have told. Yes.
Stiffness.
Mansi? Stiffness. Very good. Stiffness. Jasashwani, can you answer it right now? What the slope shows in the linear region of a stress versus strain curve?
Sir, stiffness.
Stiffness. What is the formula of stiffness now?
Load by unit deformation, sir.
Load. This is stress axis and this is strain axis. Where load is there? Stress is load by area. But I am not asking about that. I am asking about what is the formula for stiffness or Young's modulus. Okay, Mansi, can you answer this one?
Stress by strength.
Yes, stress versus strain. Very good. A change in stress versus change in strain, or simply stress versus strain, Young's modulus. Stress is because linear portion, you understand, stress is directly proportional to strain. That's all. Okay, anyways.
Hello, sir.
Yes.
Sir, that stiffness is that resilience only, no?
Sorry.
That means resilience is stiffness, right?
Resilience is what?
Stiffness. Other name
Resilience
for
and
it.
stiffness. Do you think that resilience and stiffness are same thing? Approximately same, you're saying? Resilience is the amount of energy absorbed by the material in the elastic region, right? Up to this point, at least. Before yielding, right? Before yielding, how much energy will be absorbed by the material?
Okay.
Now you got the point?
Yes, sir.
Toughness means how much amount of energy is absorbed by the material up to its fracture point. Before it gets fractured, how much energy it will absorb. Resilience means the ability of a material to absorb energy in the elastic region. Now it is clear, I think.
Yes,
sir.
Please, at least you people go through the lecture notes again. Lecture notes means you can go through the videos again. If you have any doubt, you can get it back and you can ask me doubts if you have in the coming class. Okay, now this is okay, and now okay. So this is done. Okay, fine. Now this is dislocation density. Okay, fine. As we have started the topic, that is strain hardening or work hardening. That means when we do metal working on the materials, basically cold working on the materials, our strength increases, right? So why this happens? This happens, you understand, because of dislocation density. The dislocation density is increasing. The number of dislocation in a material increases if you do cold working on the material, right? So that is the answer actually, because if more number of dislocations will be there will be a interaction between dislocation will be more, right? More interaction. They will start interacting with each other, right, during their motion. Okay, fine. Dislocation density. Here you can see dislocation density. Basically, you can use volume formula. You can use surface area, but the unit of dislocation density is basically meter to the -2. Yes. Okay, fine. So dislocation density, you can understand total length of the dislocation line per meter cube. If you are taking the length, then this is total length of the dislocation lines per meter cube, right? Or you can use like total number of dislocation line per meter square. And basically we have dislocation density is denoted by this rho, and this is 10 to the power 10 to 10 to the power 14, or some people call 10 to the power 10 to 10 to the power 15 meter per meter cube. So finally the unit will be meter to the power -2, obviously, or meters per meter square, right? And basically, okay, can you people tell me in annealed metal, if you compare a annealed metal and a cold work metal, which have high dislocation density? Let me see who can answer.
I mean, sir, in cold work metal, there is more dislocations.
Okay, yeah, nearly 10 to the power 15 meter per meter cube, or meter to the power -2, right? And in cold war, in annealed metal, it is below 10 to the power 10. Huh. Okay, anyways, and this is a very interesting fact. Just look at this one. If you take a metal of a sugar cube size, right? This is very interesting. Just a piece of metal of sugar cube size, huh? Then you can have a lakh kilometer of dislocation line. Can you imagine? Lakh kilometer of dislocation line. Right? But the interesting point is, you can understand 1 lakh kilometer of dislocation line may be present in a sugar cube size of metal. And if you are talking about atoms, how much atoms we have in a sugar cube size of metal, you can at least go to the sun. If you join them linearly, you can reach to the sun, and you can come back again to the earth. That means you can imagine how many number of atoms a sugar cube metals have. Anyways, then here I have written already cold working. Suppose you take a metal, you do cold working. Then what happens? Upon cold working, introduction of lot of dislocation in the lattice will be there. Then when a lot of dislocation will be there, what happens? The gap between the dislocation decreases in some slip plane. Suppose a particular slip plane is there and lot of dislocation are there, right? Then what happens basically? Strain field of the dislocation will interact with each other, right? Then what happens? Same strain field repels each other, leading to the restriction in the dislocation motion, right? So that will increase the strength of the material. So this is one of the way. And another way, this is already, I have a figure, you can see. This is slip plane, this is slip plane, and same sign dislocation is present. If number of dislocation will increase, they will repel each other. So that will increase the strength of the material, right? Here, this figure is showing this one. And another way is, suppose, just look at this image. There is a dislocation, there is a slip plane like this, and there is another slip plane like this. They're intersecting one another. So what will happen? This dislocation is gliding like this, and this dislocation is gliding like this. So at a point of intersection, they will interact, and they may get tangled up over there. They cannot move, right? So that will increase the strength of the material, right? Dislocation moving in one plane, which is intersected by another slip plane, on which another dislocation is moving. So they interacts, motion get restricted. So I think you people have understood now up to this, how strengthening is happening due to dislocations.
Yes, sir.
Okay. So next, we move to the next slide. This is property versus percentage cold work. Already I have explained that. Again, same figure is showing. You can see properties in this axis, and this is the percentage cold work. That means from here to here, I'm increasing the percentage cold work. I'm deforming the metal more and more by cold working. The property, you can see what is happening. The yield strength is increasing with percentage cold work. The tensile strength is increasing, but the ductility elongation means ductility is going down, elongation is going down, and reduction in area is going down. Reduction in area and elongation will show you the ductility behavior, right? Okay. So now, yeah, this is very interesting here. Another interesting point here. Hardening of non-heat-treatable alloy. See, we have certain alloys which we cannot harden them, or which we cannot strengthen them by doing heat treatment, because we understand heat treatment is a very good technique to improve the properties of a metal. Like we can improve the strength of a material, right? But there are certain alloys, certain steels are there, certain aluminum alloys are there, which cannot be strengthening by heat treatment. Acha, can you people tell me how strengthening will be there by heat treatment? Suppose you have a steel, for example. Suppose you have a medium carbon steels. Let it be a medium carbon steels, right? So how we can strengthen the medium carbon steel? By doing heat treatment. Let me see who can answer it. Or what you will do that the strength will increase? Forget about the grain refinement. Just I will forget about the grain refinement. How the strengthening will be there? Let me see. I think Susri can answer this. Susri, can you answer this? You have a medium carbon steel and you have to harden it by doing heat treatment. But you do not have to do any kind of grain refinement there. Forget about the grain refinement. The hint I can give you is transformation strengthening. Certain transformation can be done. Yes, yes. You take the steel to the austenitizing temperature. Then what you can do? So that it will become hardened. Yes, Susri, you can speak. Yeah, I know you know the answer. Okay, Mansi, can you answer this one?
Yes, sir.
Yes, can you answer this
Then
one?
we have to quench it.
Yes, you have to quench it. So when the
Yes.
moment you quench it, what will happen?
Austenite changes into martensite.
Very
Which is
good, very good. Which is a
bit-
very hard and brittle phase. Yes, excellent. In the previous lecture, also I have shown you the different microstructure of steels. Yes or no?
Yes, sir.
I've shown you the different microstructures, which are soft phase, which are hard phase. Yes or no?
Yes, sir.
Right? I have shown you the TTT diagram also, if you remember.
Yes, sir.
I have shown you the cooling curves, right? So, so you should answer these questions. Now, these are very simple questions. And if you look carefully here, it is also written. Okay, let me see who can answer this one. Sambit Swai, can you tell me by looking at this one, by heat treatment, how you are strengthening a metal? Sambit. Sambit Swai.
Yes, sir.
Yes, by doing heat treatment, how you increase the strength of a material. Just forget about the grain refinement. It is already written over here. Just look at this one. Yes, Sambit. It is clearly written over here. Sambit, can you able to answer yes or no? Just tell me. Also, Gitanjali Raut, can you answer this one? By doing heat treatment, how you can increase the strength of a material? It is already written over here. Gitanjali? Okay, Anvesh? Anvesh? Yes, can you answer the question which I have asked? By doing heat treatment, how you increase the strength of a material? The hint I can give you is transformation strengthening. Some phase transformation will be there. That is solid state phase transformation. From a solid, and the solid will be coming out, or yeah, you can say like that. Anush, just look at this one, please. and tell me.
Sir, precipitate will be formed and uh,
Very good. Precipitation will be there. Some precipitate may form. Yes, that will increase the strength. Okay, very good. Any other thing? What is this one? What is this one? What is written over here?
non-equilibrium product.
Oh, what do you mean by non-equilibrium products in a phase transformation? Okay, have you attended the previous lecture when I was discussing about the TTT diagram and I am showing you the
Yes,
different
sir.
products,
Yes,
equilibrium
sir.
products and
Sir,
non-equilibrium products? Yeah. Okay, very good.
sir,
Yes. What are the non-equilibrium?
sir, benite and martensite.
Acha, what are the Yes, benite and martensite. What are the equilibrium products?
Sir, mm, sir,
Okay, just
perlite.
forget about that. Yeah, Sushri, can you answer this one?
eh,
What is the example of? Yeah, you can mute yourself, Anvesh, right now. Susri, can you answer what are the difference between equilibrium products and non-equilibrium products during a phase transformation?
No, sir.
You don't remember? Okay, Mansi, I think Mansi will answer this.
Yes, sir. Sir, the
Yes,
product
Mansi,
is
can
a
you?
form
Yes.
by equilibrium
Sorry.
cooling that are
Yes, very good. By doing equilibrium cooling, we'll get a equilibrium product. So, what is equilibrium cooling?
cooling at a slow rate, very slow rate.
Very good. Cooling at very slow rate. Excellent. Okay, fine. So, what is non-equilibrium cooling then?
If we are cooling at a very fast rate, then it is, or quenching it, then it
Right,
is
like
non-equilibrium.
quenching. Like quenching. Yes, very good. Very good. So, examples.
The product equilibrium cooling
Examples.
product are right and perlite,
Ferrite, very good.
ferrite and
Ferrite
perlite,
and perlites, yes, very good.
and
Yes, yes.
non-equilibrium
Hmm?
cooling product are benite and martensite.
Benite and martensite, yes. Windmanstedt and ferrite is also there, huh? If you remember.
Yes, sir.
Windmanstedt and ferrite, benite and martensite, yes. Equilibrium products, you mute yourself. Huh? And equilibrium products are basically your massive ferrite, your ferrite which forms along the grain boundaries. That is, if you remember the name, that is very good. Electromorphic ferrite, right? And we have perlites. Right? These are the equilibrium products. If you differentiate between equilibrium products and non-equilibrium products are very stronger and harder. They are basically finer in grain size, right? But equilibrium products are coarser basically compared to non-equilibrium products, and the strength and hardness is less. I think everybody have understood now what Mansi told and what I told.
Yes, sir.
Okay, fine. So now you people have understood heat treatment is a very good technique where we can harden or strengthen the material. How? Because heat treatment can give you precipitations, that is called precipitation strengthening, which we'll discuss later, and we can have a non-equilibrium products, right? We can have benite and martensites, which are very strong and hard phases in the steels, which will improve the strength of the material, right? But the question is, all the alloys do not show this kind of thing, right? If you heat it, those alloys, they will not undergo any precipitation, they will not undergo any kind of transformation like this. Formation of martensite or benite will be there, right? So that means there are certain alloys or there are certain kind of steels we have where it cannot be strengthened by heat treatment, right? So sometimes it is called non-heat-treatable alloys, right? So what is the solution to this? The best solution is this one. They can be hardened by cold working. If you have a non-heat treatable alloy or if you have a alloy which cannot be strengthened by heat treatment, any suppose aluminum alloys or any alloys, you just do cold working on it. It will increase the strength of the material. I think you people have understood this one. Am I clear to everybody? I think.
Yes, sir.
Okay, fine. So now, okay, already I have explained this one. Why in hot working strain hardening do not occur? You understand, because we are dealing with very high temperature, and high temperature, the annihilation or disappearance of the dislocation will be there, right? By climbing method, or then maybe due to recrystallization also. Yes. Hello. Yes. Then rate of strain hardening. You can see in FCC kind of material, the rate of strain hardening is more as compared to HCP. Why? Because of more number of slip systems are there in FCC. 12 number of slip systems, active slip system, right? So what happens? More number of slip system means more number of dislocations will generate, and it will lead to more strain hardening. So rate of strain hardening is higher. But in HCP, only 3 number of slip systems are there, right? So strain hardening is not there because less number of slip systems are there and less number of dislocation may generate over there, right? That is the reason. Next is, okay, fine. This is a very interesting plot. Everybody should remember this plot. This is a plot between strength versus dislocation density. So dislocation density is increasing in this direction, and this is the strength. The strength is increasing in this direction. So you can see what is happening here. Suppose the plot starts from here, and just look at this one. Zero dislocation in a materials. When there is a zero dislocation in a material, the material do not have any dislocations, you can consider that is a perfect crystal or a single crystal. We have the strength of a single crystal is near to the theoretical strength, that is G by 2 pi, shear modulus by 2 pi, the maximum strength present in a material. This is here. But you can see when the number of dislocation is increasing in this direction, the strength is going down, 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 and down and down, right? And it will reach to a minimum point where strength is minimum when the density of dislocation is high. But after sometimes what happens, if you increase the dislocation density more and more, the strength will again increases like this. Okay, fine. I have explained this one. Now, can anybody tell me? Can anybody explain this again? Let me see who can explain this. Ritik Ranjan. Ritik Ranjan, can you explain this figure again, which I have explained it right now?
Hello, sir.
Yes. Okay. Okay. Ritik Ranjan. Let me give you 3 samples. Okay. Let me give you 3 samples. One sample is a single crystal, and the sample is a polycrystal with less number of annealed. For example, annealed crystal, polycrystalline but annealed, and third sample is a heavily worked polycrystalline materials. So now, can you compare that strength? Can you arrange them with increasing or decreasing order of strength? Ritik, can I ask the question again?
Sir, increase on density, strength increases, sir.
No. My question is, I'll hand over you 3 samples. One, in the first sample of steel it is a single crystal steel sample. Second sample is a polycrystal steel sample having annealed sample. Consider it is a annealed steel. And third sample is a heavily cold worked steel, which is a polycrystal, for example. So now tell me. Now you have to arrange the 3 samples with decreasing order of their strength. Yes, Ritik, can you answer this one?
Yes, sir.
Yes. The first highest strength will be of which sample? Which sample will be having high strength?
Sir, first cold work, sir.
Cold work? Just look at the image again, please. This is the strength axis. This is the dislocation density axis. Okay, you mute yourself. Bijay, can you answer this one?
Sir, can you again tell those three options?
You have
Those
three
three.
samples. The first sample is single crystal steel. Second sample is a annealed polycrystalline steel. Third sample is a heavily cold walled polycrystalline steel. So you have to arrange them with decreasing order of strength. This plot is already shown over here, which I have explained. This is the strength. This is the dislocation density.
So cold bark steel will be having the most dislocation density, so it will be having more strength, and the annealed steel will be having less. And in the middle there will be polycrystalline.
So middle one is which one?
Polycrystalline.
Polycrystalline
And
or polycrystalline?
and the third one will be
I
this.
listen my question carefully. I told you have two polycrystalline sample. Listen it carefully. You have two polycrystalline sample, but among them one is annealed, one is heavily cold walled, and the third sample is your single crystal steel.
Okay.
Okay, Shushri, can you? Okay, you mute yourself. Shushri, can you answer this one? You have to arrange themselves with decreasing order of their strength.
Sir, a heavily cold work still.
Will be having high strength.
Yes, sir.
Just look at this image. Just look at this image.
Sir, single crystal of steel fast.
Very good.
Hello.
Yes. Yes.
Second,
Yeah, next.
polycrystalline annealed polycrystalline middle.
Very good. Yes. Next.
And
Last one.
cold polycrystalline middle.
Cold war, not cold.
Cold work polycrystalline.
Wait, how can you justify? But by looking at this figure.
In single crystal steel, there is
Yes.
no dislocation.
No dislocations. Very good. Yes. So that's why the
After-
strength is how much? G by 2 pi. That is theoretical strength. Already written over here. Yes. Then next.
Then due to annealed dislocation at a high temperature, dislocation decreases. Density
Decreases or dislocation is increasing. Just look at this one. Annealed crystal have some amount of dislocations, obviously.
dislocation increases.
Yes. What is happening to the strength?
Strength decrease.
Decreasing. Yes, it is going down. Very good. Then
After that, in
cold war metal have a lot of dislocations. Dislocation density is very high. So what is
very
happening
high.
again?
Strength will increases.
Yes, very good. You people have understood, or shall I repeat this one? Susri, I think you have understood now.
Yes, sir.
Bijay, what about Bijay?
Yes, sir.
Bijay, can you explain it again? Let me see. Can you explain this again? Yes.
Sir, the single crystal will be having the most strength. Means
How can you justify single crystal? Tell me the figure. Just talk about the figure. Yes.
Means at the top, sir.
At the top.
Because it has less dislocations.
Less dislocation or zero dislocation? What is written over here? Just read it.
Sir, zero dislocation. And
Single crystal is a single crystal have any dislocations?
No, sir.
It is a completely defect-free crystal. Yes or no?
Yes, sir.
Single crystal have any grain boundary?
No, sir.
Yes, it is a defect-free. No? It is a grain boundaries and the defect. Okay, now can you explain it? Yes.
Then again, polycrystalline material has more
I won't
dislocation.
talk about any polycrystalline material. Just look at this figure and tell me.
Means then again at the downward slope,
Yes, slope is going downward. Why?
sir, due to increasing dislocations.
Yes, very good. This is the direction of dislocation density. Dislocation is increasing, so the strength is going down. Yes, next.
Due, due to there will be polycrystalline metal for this, and then on increasing dislocation density, the strength will again increase. That is for
Yes,
cold
very
work
good.
room.
Very good, very good. Why I have compared between single crystal and cold work metal and annealed metal? Because you understand, single crystal means no dislocations. Annealed metal means few number of dislocations are there, and cold work metal means lot of dislocations are there. That's why I have compared that one with this one. I think you have understood this one, right? Then there is a very
Hello, sir.
yes, yes.
Sir, will temperature will be any factor here?
There is no temperature here. Is there any axis showing temperature here?
Means
This is a simple strength versus number of dislocations. How
so, sir,
strength is changing on the basis of number of dislocation present in a materials. If a material do not have any dislocation, the strength is maximum, which it is showing here. Just look at this one. Maximum strength, because this is the strength axis. Strength is 0 and strength is increasing in this direction. This is the 0 dislocation. Dislocation is increasing in this direction. The plot starts from here. Plot starts from here is it is the maximum strength you can see. Right? There is no dislocation here. 0 dislocation you can understand. Now the dislocation is increasing in this direction. That means the strength is going down. You can see the strength is decreasing. Right? Slowly, number of dislocation is increasing. So strength is more decreasing. And after sometimes when the dislocation is more and more and more, the strength is again increasing. Now you got the answer?
yes, sir.
There is no role of temperature here. This is cold working below the recrystallization temperature. Temperature may be there, but it is low. It is below recrystallization temperature. There is a formula that is shear stress as a function of dislocation density. Tau is Kb root over of dislocation density. This is a formula. B is Buzzer vector. Rho is the dislocation density. Tau is the shear. What is tau here? The shear stress required to force two dislocation past each other. When two dislocation want to move across one another, this is the shear stress required. So can anybody tell me if the shear stress required to force two dislocation past each other, so it is depending upon what exactly? Can anybody tell me by looking at this formula? Shear stress required to force two dislocation past each other, like this, for example. This one. And this one. So it depends upon what? Shear stress will be more or less. It depends upon what? Just look at the formula.
So dislocation density.
Yes, dislocation density, very good. So if dislocation density will be high, so shear stress required to force two dislocation past each other will be more or less. If dislocation density more, obviously, because they are linearly related. So more is the dislocation density, more is the number of dislocations per unit area or per unit volume of the materials. So shear stress required to force two dislocation past each other will be more. I think you people have understood now. Okay, so now there is an interesting relationship between the distance between the dislocations and the dislocation density. You can see L is the space between the two dislocations, and this is the dislocation density. So L is equal to rho to the power minus 0.5, or you can write like this: 1 by square root of dislocation density. So can you people tell me now, this relationship is saying what exactly? If dislocation density will be more, what happens to the spacing between the dislocation?
So inversely proportional.
So what will happen if dislocation density will be more in a material?
The spacing will decrease.
Obviously, the spacing will decrease. This is a relationship, right? Inversely proportional. So more dislocation you have in a material, less is the distance between the dislocations. A space between the dislocation will be less. So if the space between the dislocation will be less, you understand what will happen. So now this is suppose this is a grain. You have a square grain. So what happens when more number of dislocations generate in a materials, they will make a cell kind of thing. These cells are nothing but the dislocations arranging themselves in a grain. So this is called cell structure. Again, I am repeating, when we have a lot of dislocation in a materials, these dislocations try to arrange them in form of a substructure or in form of a cell. They form a cell. This kind of cell they will form. This is not grain actually. This is entire is a grain, but these small substructures are looking like a grains, but these are actually arrangement of the dislocation in form of a cell, right? And this is an interesting point. When we are cold working, only 10% of the cold work energy is stored in the material, which will help in the recrystallization basically later. So only 10% of the cold work energy is stored in the materials. Other energy will be lost in form of energy and sound, like heat energy and sound. Okay. So now there might be a question how dislocation generate in a material, right? That is called Frank-Reed source. Frank is one person, Reed is another person. Both have developed this concept. How more number of dislocation generate. This figure is showing everything. Already, I think I have explained this one in earlier class. If you remember, you can see this is A and B. These are, suppose this is one precipitate, this is another precipitate. Or suppose this is one dispersoid and this is another dispersoid. Or this is some pinning agents, some particles, some inclusions, for example. This is a dislocation. Or dislocation line, you can say. This dislocation line is moving like this. And the moment it will reach, it will get pinned up by this A and B particle. So first image is 1. This is a image 1, first image. What is it showing? It is showing that 2 particles in the matrix is pinning the dislocation, right? But you are still applying load or stress, tau. Here it is written, you can see the arrow mark of tau. What will happen? Since the dislocation is getting pinned up by these 2 points, but still it want to propagate in this direction, but it cannot propagate. So what happens? It will take a shape of this one, like this. You can understand this is kind of a bowing of dislocation. Dislocation get bowing here. This is kind of an arrow and bow. Now what happens? This will happen again. You are applying stress, so this will bow like this. This is the first. This is the second bowing, and this is the third. Again, what happens? It will bow again like this. This is the image up to this much, up to here. From here to here, more it will bow like this. Now when this will reach to this stage, this is the first stage, this is the second stage, this is the third stage, and fourth stage is this one. Now what happens when the dislocation will reach in this stage? This is one sign dislocation, this is another sign dislocation, opposite sign dislocation, or dislocation with opposite sign is present. So what will happen? If dislocation will opposite sign will be there, what happens basically? Vijay, what happens if dislocation of opposite signs will be there? Or opposite Berger vector will be there?
Sir, they will cancel each other.
They will annihilate each other, right? So what happens? The annihilation is happening and finally a loop will form. You can see this is the final loop. You can see. So dislocation will come out, a new dislocation will form, and dislocation will form a loop. New dislocation will come out from that. So in this way, many dislocation will coming out from the Frank-Reed source. Okay, let me show you another image, beautiful image. Here I have. You can see this is a pinning agent, this is a pinning agent. Any precipitate or dispersoid or any inclusions, they're precipitating, they're pinning the dislocation here. And stress is applying, you are applying stress. So it will convert into this first. So this is stage 1, this is stage 2. Again, it will become stage 3, and stage 4 is like this. The moment it will form stage 4, what I told, you can see opposite sign dislocation. This portion is having one Berger vector, this is having opposite Berger vector, or you can say this is having a, suppose, negative positive dislocation, this is having a negative dislocation, for example. So they will annihilate each other. Finally, a loop will form like this around the dislocation. Around this spinning agent, there will be a dislocation loop, right? So now, you can compare the cold working versus annealing. Okay, so when we do cold working on a materials, what happens? Strain will be there in the materials, dislocation number will increase, ductility decreases, strength increases, right? So these are the things happen in the cold work materials. Strain increases, dislocation density increases, strength increases, but ductility goes down. But suppose still you want to deform your materials. What happens? You have to do annealing on it. So the moment you do annealing, what is happening? Strain will decrease, dislocation number will decrease, ductility will increase, strength will decrease again, right? Okay, how many of you have remembered the annealing process after cold working? What are the different stages of annealing? After cold working, when you do annealing, what are the different stages?
Sir,
What are the
recovery.
Yes, recovery. Somebody is saying recovery. Okay, recovery happened at a low temperature, but still you are rising the temperature. What will happen after that? After recovery?
Recrystallization.
Recrystallization. Very good. And after the recrystallization, what happens finally?
Then growth.
Grain growth will be there. Very good. So 3 stages will be there in the annealing process. Recovery is the first stage, which happens at a low temperature, but still you are rising the temperature of the material. Then recrystallization will be happening. Finally, when the temperature is very high, grain growth will be there. So recovery, then recrystallization, then grain growth will be there, right? So due to this is happening. Strain will be reduced, dislocation number will be going down, and finally ductility will increase, the strength will decrease, right? I'll show you some interesting figure. You can see this one. So this is the recovery stage. Let me see who can figure it out. What is happening in the recovery stage of annealing of a cold work metal? Can you people figure it out? What is happening? Okay, what is this first stage is showing? This first stage is showing cold work metal. Yes or no? Why this is a cold work metal? Can you will tell me?
The generation of more dislocations.
Yes, due to presence of lot of dislocation in the material, we can say this is a cold work metal. So you are rising the temperature during the recovery stage or during the annealing stage. You are doing annealing on this now. You are doing annealing. So temperature is rising. What is happening here? Can anybody tell me? By looking at this figure.
Sir, that dislocations are removed.
Dislocation. What is happening to dislocation? Dislocation.
They're annihilating themselves.
Annihilating. Just tell me the position of dislocation is here. Then the position of dislocation is changing. So what is happening to the dislocation? Mansi, can you tell me what is happening to the dislocation?
So the density increase.
Dislocation is, suppose this, I'm considering this dislocation. This dislocation is here, now dislocation is here. So what is happening? Huh?
Rearrangement of dislocation.
Rearrangement, okay, that is fine. But what is happening to the dislocation? Why they are rearranging?
To annihilate each other.
Annihilate each other? They're gliding. Just look at this image. They're gliding or not?
Yes, sir.
Yes.
They're moving. Moving means dislocation glides, no? They're gliding right now. This is the initial position. They're gliding. So it has glided to this position. This dislocation has glided to this position, for example. So when you are rising the temperature, dislocation start gliding right now, right? So when they are gliding, then what is happening? Can you tell me further? Just look at this image. Otherwise, this image and this image. Now tell me what is happening here. Can anyone tell me what is happening in this figure and in this figure? Carefully look at the image and tell me. The hint is number of dislocations.
Number of dislocations are decreasing.
Decreasing. Why they are decreasing? And how they are decreasing?
Sir, by their okay.
God, you just look. You people are not attending previous lectures. I think you have attended. All of you have attended the previous lecture. What is this picture is showing? What this picture is showing?
Because a positive and a negative dislocation on a same sleep plane.
Can you repeat, Mansi? What is happening here?
After gliding of dislocation, a positive and a negative dislocation on the same sleep plane, they will attract
Yes.
each other and try to cancel
Yes,
out.
they will annihilate. They will get dislocation. Annihilation will take place. They will get disappear. Very good. So, Vijay, can you answer again? What is happening here and here?
Sir, the opposite dislocations are attracting towards
Themselves, yes. Then
and they are annihilating.
how they are annihilating now? If they will attract each other, and finally, how you can say they are annihilating each other?
Sir, so due to that compression and tensile field between them.
Okay, mute yourself. Susri, can you answer this one? If opposite sign dislocation attract each other, how they get annihilated on a same sleep plane?
Sir, by arranging linearly.
Arranging linearly, they are annihilating means there will be no dislocation anymore. They will get disappear completely. How they will get disappeared? Yes. What is a dislocation? What is the definition of a dislocation? How you can define a dislocation?
Sir, change in continuity of atoms.
Oh God, you are defining a dislocation change in discontinuity.
Sir, displacement.
Dislocation is a displacement. Oh God, what you are saying? Yeah, Mansi, can you define a dislocation? Yes, it is a.
It is a line imperfection.
It is a line imperfection, but what is the definition? Exact definition of dislocation? What is this? In this crystal, what is this one?
An extra.
It is an extra half plane of atom. That is the definition of dislocation. Dislocation is a line defect or linear defect. It is nothing but an extra half plane of atom. Vijay is saying something else and Susri is saying something else. Vijay, what is the definition of dislocation?
Sir, extra half plane of atoms.
But why you are saying something else?
Sir.
Okay, now can you give now all the hint I have given you? Now how dislocation get disappear? Okay, Mansi, can you answer this one? How dislocation get disappear? How they get annihilated?
The compression field of one dislocation and tension field of another dislocation.
Okay, fine. Anyways,
The
cannot
seat
answer.
When we heated in an unleading process.
Yes, I think Subhashri can answer this one. I think Subhashri already have answered this one earlier. How, Subhashri, how opposite sign dislocation annihilated themselves when they come closer?
Sir, due to attraction of compression and tension force.
Attraction, compression, what you are saying? Just look at this one. Okay. Just can you do you people can you people see this one? This figure, this part only. This one. It is visible to everybody.
Yes,
Yes,
sir.
sir.
What you are saying? This what you can see this here?
Sir, opposite dislocations.
Opposite dislocations, right? One is T, one is top part is inverted, bottom part is T, right? So now this total will be what now? If you consider this total, this is what I can call.
Single plane.
This is a single plane of atom. There is no extra half plane of atom right now. Now you people understood? Now you people understood, or shall I repeat?
Yes, sir.
Dislocation is an extra half plane of atom. If you have a dislocation on the top and a dislocation on the bottom in a same line, so this is not an extra half plane of atom. This is a completely single plane of atom now. So do you find any dislocation now? Subhasri?
Sir, in which figure?
In which figure? Look at this one. This part only.
No, sir. That is perfect crystal single gate.
Vijay, can you explain again how dislocations annihilate themselves?
Sir, when two opposite dislocations and attract with each other, they annihilate themselves.
How they annihilate?
There will be a it will be a complete single plane of atom.
Yes, very good. They will become a complete single plane. That means there will be no any extra half plane of atom will be there now existing. I think everybody have understood now. Anvesh Purohit, can you answer again? Anvesh.
Yes, sir.
Anvesh, can you answer what is happening in this? What has happened in this figure? If you compare this figure, and this figure, what is happening in this figure and what is happening in this figure? Okay. Yes.
Sir, annihilation is taking place.
Okay. Very good. Annihilation is taking place. Annihilation of what taking
Sir,
place?
sir, dissolution.
Annihilation of what? What is taking place?
Sir, dislocations.
Dislocation. What kind of dislocations? Oh, we have same kind of dislocation here in this material. All are edge dislocations.
No,
but
sir.
Yes. What is the difference here? Yes. What is the difference here?
Sir, sir, actually, sir, the sign are opposite.
Yes, sign are opposite. So which kind of dislocation is getting annihilated here? You are saying? Just look at the image and tell me which kind of dislocation are getting annihilated. Look at this figure, then this figure.
Yes, sir.
Here, which kind of dislocation has get annihilated?
Sir,
Okay, let me expand this one.
sir,
Okay, finally compare with this one or this one. Then let me see which kind of dislocation has get annihilated.
Sir,
Okay, Gitanjali, you mute yourself, Anmesh. Gitanjali, can you answer? A lot of discussion already we have right now, but let me see. Gitanjali,
Yes, sir.
yes, how the dislocation are getting annihilated?
Sir,
They are
dislocation
getting
means
disappeared.
Sir, dislocation means there is one extra half plane of atom,
Okay,
and
very good. Yes,
yes, sir, in this case there is one dislocation on the upper half and one dislocation on the lower half of a plane.
very good, very good. Yes, yes, yes.
Sir, sir, they get cancelled. Means, sir, there will be no extra half plane present.
Very good, very good, very good. So that means opposite sign dislocation is getting annihilated. Yes or no?
Yes, sir.
Anvesh, you understand or Anvesh, can you answer again? Which kind of
yes,
dislocation
sir.
is getting annihilated?
Sir, sir, opposite sign of dislocation are getting
Yes.
annihilated.
Okay. Now the question is why they will get annihilated? Why opposite sign dislocation will get annihilated? Yes, Anvesh. Why opposite sign dislocation will get
Yes, sir.
annihilated? Hmm.
Uh, Sir, because of
Hmm.
sir extra uh, sir because sir because sir this will form a complete single plane.
Yes, very good. It will become form a complete single plane of atom. Okay. That means which plane of atom will be not there now after forming a single plane of atom? After formation of a single plane of atom, which plane of atom will be now missing?
Sir
Hmm?
sir the half plane.
Yes, half plane of atom will be missing. Very good.
Yes, sir.
Okay, I think you people write a
Sir,
assignment. I think you
sir
unless
the
until you
half.
do an assignment. Yes, yes, Anush, I understand. Yeah, you mute yourself. Write an assignment. What is dislocations? Quickly write it down. Put your date, then mention the date, today's date, and write the assignment one. It is what is a dislocation. Hmm. Second question is what are the different types of dislocations with their images. You have to draw the images. What are the different mechanisms by which dislocation get annihilated in a material? What are the different mechanisms by which dislocation get annihilated in a material? What are the different mechanisms by which dislocation get annihilated in a material? You have to draw the images. And just below the images, you have to write the important point only. Completely, you have to draw the images. Cartoon diagrams. Huh? You have to draw cartoon diagrams of that. What are the different strength fields around the dislocations? What are the different strength fields or stress fields around the dislocations? What is a sessile dislocation? What is a glissile dislocation? What is a sessile dislocation and what is a slide dislocation? These are the assignment of this. And you divide the whole class into two groups.
Sir, last question.
What is sessile dislocation and what is glissile dislocations? So you divide the whole batch into two groups. First roll number 2, the middle is one group and another. So you have to submit the assignment in two groups only. This is a group assignment. Yes, and the question is how dislocations moves in a material. What are the different ways? What are the different ways by which dislocation move in a material? So it is a group assignment. You have to submit in a group. So you discuss among yourself and reach to the conclusion and write the assignment. Somebody has to write finally. You try to collect the things in a group and you try to present it in a group form, right? So group 1 and group 2, only 2 assignments. You have to submit in 2 groups only. Okay, anyways. So you people have seen that this is a work hardened metal, cold work metal. Lot of dislocations are there. So some dislocation are T and inverted T, opposite sign dislocations are there. And when you rise the temperature, what is happening? Dislocation is gliding. The same sign dislocations are moving towards each other. They are cancelling one another. Here you can see. This is the point here. Inverted T and T. They're cancelling each other because it is forming a single plane of atom right now. Here they will cancel each other. So finally, what is happening? Opposite sign dislocations cancel each other, or you can say they are getting annihilated from these materials. Finally, we will left with same sign dislocation. You can see this is the condition. Same sign dislocation, and same sign dislocation arrange themselves one below another like this. One below another, they are arranging themselves. Finally, this is the situation. This is a kind of polygonization called. This term is called polygonization, and due to arrangement of dislocation like this, we have tilt boundary. You can see this is a tilt boundary. The single initial crystal, you can see this is single initial crystal is getting tilted here. It is getting tilted here. If you remember, when you push dislocation into a single crystal or a single grain, they will get tilted. It will form a tilt boundary. So you have tilting will be there. This is a small angle boundary. Right. So this is a small grain, you can, or subgrain, you can say. This is a subgrain. This is a subgrain here. This is a subgrain. Right. This is a subgrain. I think you people have understood the recovery stage. And in some concepts, they have told that during recovery stage, diffusion of atoms will be there, and some atoms will start arranging between the dislocations. Suppose one dislocation is present above and one dislocation is present below, and they are far apart. Due to diffusion of the atoms will get sit in the middle portion, and they will make the plane complete. Like this way, dislocation can get annihilated also. There are certain concepts. Then, dislocation glide video. Okay. Then finally, growth after recrystallization. So you can see, can anybody figure it out what is happening here? Can anybody figure it out what is happening here? What is this image is showing? Can you compare this part with this part? What is happening here?
Grain growth.
Grain growth. So here what happens? The grains have recrystallized already. Okay, how recrystallized grains looks like and how deformed grain looks like, how you can differentiate them? Suppose you are doing rolling on a metal piece, how the grains will looks like, and after recrystallization, how the grains will looks like. Oh God, you cannot able to answer this one. Simple answer.
Grains are
Initially, your grain is suppose equiaxed grain. You do rolling on it. How it looks like now?
It will elongate due to.
Yes, it will elongate in the rolling direction. You will find elongated grains. right? So after now your cold work metal have elongated grains. So now you're doing recrystallization. New recrystallization means formation of new strain free crystals will be there. There will be no defect will be there, or defect will get annihilated, right? So now the after recrystallization, which kind of grain will be there? Just look at this one.
Spherical.
Spherical?
Equivalent
Yes, sir.
grain.
Equivalent grain, very good. Again, equivalent grain will be there.
Original.
Yeah, original grain is already, I told you, that is equivaxed. Have you ever seen any spherical grains? I have never seen any spherical grains.
No, sir. No, sir.
So after recrystallization, you are getting a equivaxed grain again. So what is happening here? Just look at this image and tell me what has happened. What has happened? The grain growth has happened. Yes or no? Can you able to see the bigger grains? Can you able to see the bigger grains here?
Yes, sir.
The grain has coarsened up, become bigger. So recovery has happened, then recrystallization, then grain growth has happened finally. Fine. Okay, this is done. So so basically what happens in the recovery stage? In the recovery stage, restoration has happened. The properties has come back into the materials. Suppose initially the material is ductile and the material is having high electrical conductivity. Due to cold working, the ductility have reduced, the electrical properties, that is conductivity, has reduced. But due to
Hello, sir.
recovery stage, yes.
Sir, can you wind up? Dinesh sir is waiting for class.
Yeah, let him wait. I will take 2 minutes more. So during recovery stage, what happens? The material has recovered. Means they have restored its properties. The mechanical properties, the electrical properties had come back into the materials. It will become ductile somewhat and it will become electrically good conductor now. But in recrystallization stage, what happens? New strain-free crystals will form. Right? Strain-free crystals means there will be no strain in the new grains. Right? And finally, the growth will happen. The new, smaller new crystals which has formed, they will become bigger and bigger. Right? Okay, so I will end this topic here. Okay, you people can leave.